Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be going over E2 reactions. We've started doing podcast format as well, so for those who'd like to reinforce these concepts on the go, please check that out, and any mechanistic stuff will solely be in the video. I'll also link the podcast link down below as well. Before we start, let's define a few things. So the alpha carbon is the first carbon that is attached to the functional group. And in this diagram, the alpha carbon is shown in the red alpha symbol right here. Now the alpha hydrogen is the hydrogen attached to the alpha carbon, which is depicted in the blue alpha symbol. The beta carbon is the second carbon atom in the chain next to the alpha carbon. Now that's indicated in the blue beta. Now notice how that there can be more than one beta hydrogen. One to the left of the alpha carbon, as well as one to the right of the alpha carbon. Now this will play a role a little bit later, which we'll get into. Now this right here is what a general E2 reaction looks like. In the elimination reaction, a beta hydrogen is removed together with a leaving group, which then forms a double bond. So as you can see right here, the base takes away the beta hydrogen, forms a double bond, and then the leaving group leaves. So in the E2 mechanism, the E2 process, a strong base removes a proton on the carbon next to the carbon with the leaving group leaves, and then forms a double bond. Now this all happens in one step, much like a Sn2 reaction, which we called a concerted reaction. Now because the E2 reaction involves two chemical entities, in this case a base and a substrate, it is also said to be bimolecular, just like Sn2. So let's move on to some factors that affect E2 reactions. We can look at the substrate, the base, and the leaving group. So with the substrate, E2 reactions prefer tertiary substrates over secondary substrates over primary. Now this is due to the stability of the alkene. The more substituted the substrate, the more stable the double bond. Now we mentioned earlier that the Sn2 and E2 reactions share similar traits, such as being concerted reaction and being bimolecular. Now this particular indication right here, the substrates, this is what differentiates between the two. And just remember that the tertiary substrates do not undergo Sn2 because of steric hindrance. Now with bases, a strong base is required for E2, one that accepts a beta proton, which is part of the rate limiting step. And then the last one is the leaving group, which also requires a good leaving group, because it is part of the rate limiting step, so a good leaving group will lead to faster reactions. Alright, so part of the E2 mechanism is to abstract the hydrogen atom on the carbon beta to the carbon of the leaving group. Now if there are more than one hydrogen atoms to abstract from the beta carbon, you will end up with a mixture of products. So we have a rule that we follow, it's Zaitsev's rule, which predicts that the elimination reactions major products between the mixture of products will be the more substituted alkenes. So we have Zaitsev's product, which will be the one that's more substituted alkene. E1 reactions, which we'll talk about later, will always follow Zaitsev's rule. E2 reactions will follow Zaitsev's rule with a few exceptions. Now if we look at Hofmann's product, that occurs in each reaction when a bulky base is used to abstract the beta proton that is least sterically hindered. This will result in the least substituted alkene, and we'll revisit the Hofmann product a little bit later in the video, but first let's focus on the Zaitzev product. Alright, so this right here, we'll look at this example on the top. So we have a 2-chlorobutane as the starting material. So as you can see, you have two beta hydrogens, one on the left of the alpha carbon, one to the left of the alpha carbon, and one to the right of the alpha carbon. So let's abstract the beta hydrogen on the left first. So we see that we have a hydroxide ion, again, which is a strong base, and that is this right here. That will be abstracting the beta hydrogen. Double bond will form, as you can see right here, and then the leaving group leaves. And then we end up with a mono-substituted alkene. So as you can see right here, this mono-substituted because it only has one alkyl group. Now if we look at the bottom example, again we have 2-chlorobutane as the starting material. Same thing, we have two beta hydrogens, but let's abstract the beta hydrogen on the right. So again, we have a hydroxide ion, which is a strong base. It will abstract this beta hydrogen, double bond forms, and then you have the leaving group leaves. As you can see, the product is a di-substituted alkene, and the bottom product will be the Zaitsev product, just because it is the more substituted alkene. We know this is a di-substituted alkene because it has two alkyl groups, one right here and one right here. All right, and so E2 and SN2 reactions compete with each other. It's because they both require leaving groups, as well as SN2 requires a good nucleophile, while an E2 reaction requires a strong base. Oftentimes a nucleophile can be a strong base, but with that in mind, we can minimize the substitution portion by introducing a bulky base. So some examples of bulky bases that are used to push a reaction towards E2 is shown in the study aid right here. We have tert butoxide as well as lithium diisopropyl amide, or amide. It's also known as LDA. The steric hindrance will often stop the bulky base from abstracting the proton that leads to the more substituted alkene. And with this in mind, the bulky base will again abstract the less hindered proton, forming the least substituted product, which, as we mentioned earlier, would be the Hofmann product. Now we can see this demonstrated in this example right here. All right, so in the first example, as you can see right here, we see that the usage of a non-bulky base in the E2 reaction. Again, in this, we have a hydroxide. And in the top portion, we'll see that the hydroxide is abstracting the beta hydrogen to the left of the leaving group. The double bond forms, and then the leaving group leaves. The product here is a tri-substituted alkene. And as you can see, this is tri-substituted because there's 1, 2, 3 alkyl groups. Now if we just blow this up a little bit more. So as you can see right here on the bottom portion, we do have another strong base, a hydroxide, abstracting the beta hydrogen to the right of the leaving group. The double bond forms, and then the leaving group leaves. Now if we do that, we have a di-substituted alkene, again because we have two alkyl groups, one right here, one right here. The one that has the more substituted will be the Zaitzev product, which is the one on top, and then that will be the major product. Now let's put this one away and let's look at this one right here with a bulky base. All right, in the second example, we can see the usage of a bulky base in a E2 reaction. And in this case, we'll use a tert butoxide as a strong base. So in the top portion, we'll see a tert butoxide abstracting the beta hydrogen to the left of the leaving group. The double bond forms, and then the leaving group leaves. Now this particular proton is more sterically hindered due to having two alkyl groups around it, the methyl group right here as well as the ethyl group. The product will not be the major product due to the steric hindrance, but we do end up with a tri-substituted alkene. One alkyl group right here, one right here, and one right here, so that's the tri-substituted alkene. Now in the bottom portion of this, we see the tert butoxide, again the bulky strong base, abstracting the beta hydrogen to the right of the leaving group. Double bond forms, and then the leaving group leaves right here. Now this particular beta hydrogen is less sterically hindered due to only having one alkyl group around it, which would be the ethyl group right here. The product will be a major product just because it's easier for the bulky base to abstract that one. Even though it is not the more substituted one, it will still be the major one just because it's easier for the base to abstract that beta hydrogen. So we do end up with a di-substituted alkene, and again that is the Hofmann product. Now we had mentioned earlier that SN2 and E2 reactions have some similarities when it comes to being a concerted reaction. SN2 reactions require a backside attack, and E2 reactions require a coplanar arrangement of the orbitals. So we had mentioned that the beta proton and then the leaving group must be anti to each other, meaning that 180 degrees from each other, the reaction would occur much faster. So as you can see in this study aid right here, the beta proton, which is this right here, is 180 degrees from the leaving group in the Newman projection. Now the base is as far away from the leaving group as possible. The transition state is also lower in energy in the anti-periplanar conformation than is the next conformation we'll talk about a little bit later. And we call this where the leaving group in the beta hydrogen that's supposed to be abstracted, anti-periplanar conformation. Now, as we look in this conformation right here, when the beta proton, which is supposed to be abstracted, and the leaving group are on top of each other, as you can see in this Newman projection, we also call that eclipsed. The orbitals are aligned, but this time they're what we call Syn-periplanar conformation. Now this is unfavored due to the negatively charged leaving group, as well as the negatively charged base, which will, because they're both negatively charged, they'll repel each other. And then another reason is that in the transition state, the eclipse interaction also results in a higher energy, which is unfavorable. Now the reason why this is all important is because when you do certain problems, you'll have to make sure that the leaving group as well as the beta hydrogen are abstracted. The beta hydrogen that is being abstracted are anti to each other to ensure that you'll get the correct alkene. Now this concludes our E2 video today. Hit that like button, subscribe button, support the channel, share it with your friends who need help with organic chemistry. In the next video, we'll be doing E1 reactions. We're putting up more videos, so let me know down below what you'd like to see. Social media links are down below, and as always, just remember, you gotta go.